Okay. The last time I asked you to do a little bit of a task, did you watch the YouTube videos? Okay. Probably some. Because most of you don't have the big or the background in fluid dynamics, we will cover fluid dynamics in detail. I also provided videos on YouTube for you to get an additional background. And during the lecture, we will discuss the equations and how we get to the equations. So it's somewhat similar to the YouTube videos, but I encourage you to ask questions also concerning the questions you will have to answer for the examination. So before we start, what we will cover in fluid dynamics, first of all, you see the slides. Yes, okay. First, we will cover some basics, then the conservation equations, then constitutive equations, like how relate different field properties, like the strain and the stresses. Then I will give some motivation towards acoustics. So acoustics is more or less a special case of fluid dynamics. So therefore we cover it partly in fluid dynamics, how acoustic relates to fluid dynamics. And then there are some questions for you to get feedback on your learning progress. And these questions will also be the hand-in assignments you do. Probably we start with the questions you will have to answer. During the hand-in assignment, it's question Fluid Dynamics 1, Fluid Dynamics 3, Fluid Dynamics 4 and 5. So 1, 3, 4, and 5, and we will probably just jump into the questions. No, doesn't work. So at the end of the whole chapter, there are the questions. And so you will have to hand in for the lecture the first question. So explain the difference between Eulerian and Lagrangian description of physical fields and provide at least 3 examples. The examples are in your textbook. Just look them up and you will get some idea what it is. You also have to answer the third question. Use Reynolds transport theorem to arrive at the conservation of mass for fluids. So it's more or less what we will cover in the next 10 minutes. Yeah, probably. Then the fourth question is the conservation of momentum is given in operator notation. Rewrite this equation with Einstein's index notation. So look the conservation of momentum up in your lecture notes, and I will get into details what's Einstein's index notation and what's operator notation afterwards. Please, for me, it is kind of basic doing this. So if I miss or didn't explain it in detail so that you understand it, please ask afterwards what the different notations are. But usually the operator notation is like, all know the nabla operator, or like all this functional analysis stuff from math. And Einstein's index notation is really you write the indices of the operators in a different way. So that's more or less what we do. And then the fourth question, which is here the question number 5, you will have to hand in, is how is entropic and homotropic state of a fluid defined? It's covered in the lecture notes. And yeah, I will point it out when we are there. So you can just look this up, and yeah, you will be fine. So these are the 4 questions you will have to hand in for your examination of the fluid dynamic part. So this is question 1, 3, 4, and 5. Everyone okay with that? Okay, so perfect. So that's the examination. And so any questions on that? Oh, okay, perfect. And you can hand your submission in via the Teach Center. So that's how it looks in the Teach Center, and then here under submission, just upload your handwritten examples. And it's due to the 5th of November. So yeah, it's not a big hurry, but yeah, the questions are also quite interesting if you cover it then right away. So today I think we will cover question 1, 3, and probably 4. Yeah, question Fluid Dynamics 5 will be covered probably next week. So to get an impression where we get to the questions. Okay. So as said, we will start with the basics, then doing the conservation equations, then constitutive equations, and then some outlook towards acoustics from a fluid dynamics perspective. What I would like to give you as a tool that you can interpret computational aeroacoustics calculations with the relevant equations, so the conservation equations and the constitutive equations, and you can explain the physical effects there. So this is the goal where I would like to have you, and therefore we will discuss conservation equations, dimensionless numbers, and Helmholtz decomposition. The fluid dynamics part will be taught by me, and that's more or less how it works. All good with that? Okay, perfect. And there is what is good for. In the chat, I already posted a publication which was went online yesterday, and this is more or less about what it is good for. Check out this publication, and it's about fan noise simulations and what physical fluid dynamic effects can occur there, how we can measure these flow quantities. So there's also some section about validation and what type of measurements we did for this particular fan, and how to select a simulation model. there is a specific simulation model given there, which is a large eddy simulation. During the practical course, you will get the knowledge what a large eddy simulation is, and that's more or less it. And here, you see a flow visualization. It's the Q criteria. The Q criteria is a criteria which relates vertical structures under the context of how much strain is induced in a fluid element. So this is more or less the Q criteria, and this is visualized here. So that's what it is good for learning fluid dynamics in this course. And for some details, go to the link of the latest publication from our institute, and you will get some additional knowledge. Okay. Any questions on that? Nope. Perfect. So I think everyone is fine. And then welcome to today's lecture. First, I will cover some basics in continuum theory. I also covered this in the YouTube online course. Basically, we assume that we can apply continuum theory. This means that the Knudsen number is very small, which more or less means that if a particle travels within the matter or the size of control volume you are using, that the particle, before it pushes the boundaries, it already pushes other particles. That more or less, if a particle travels within your volume you are watching, it will meet other particles. And this is more or less how you can impose continuum theory, that you know that the Knudsen number is well below 1. And if this applies, then state variables like the density are functions of space and time. And these functions are macroscopic functions, which means that you have more or less an average over a certain domain. As you see here in this graph, here is on the y-axis the density, and on the x-axis more or less the cube or the volume you are looking into. And if the cube is very small, there is either a particle or not. And if there is a particle, the density is probably high. And if there's no particle, the density is low. So therefore you have a range of densities for very tiny subvolumes. And as we go more to the macroscopic scale, this density is more or less an average representation, so a macroscopic function. So the very tiny spatial fluctuations of the fluid density then more or less average out, and this is how we come to the continuum theory in a very pragmatic way. So probably if you're asking a physicist, he will tell you a totally different story, but the essence is more or less the same. Was this understandable? Okay, so the short message is that we apply continuum theory, and then we can use for state variables like density, velocity, forces and other stuff, that we can use macroscopic functions for this. Okay. In the context of continuum mechanics, we can define a total change of a scalar quantity, like the density here. All of you already heard this more or less the total derivative in math and how you can define it. So the total derivative is the sum of spatial derivatives with respect to the parameters. The parameters here are the time and the space coordinates. And this is how we define a total change of a scalar quantity. You can also define this total change of other tensor quantities. It's very similar and just straightforward. And if we have a fluid body here, B, and we have a fluid particle R, then we can define, based on the total change, the material derivative or the substantial derivative. It's just two terms that mean the same, and this is done by kind of putting the dt here on the left side, and here then we have the material derivative of the density, and the material derivative says, okay, when we have the total change of the density with respect to time, it's a sum related to the partial change with respect to time and a convection term. So this is purely the time change, and this is convection there. That's the difference between the material derivative and the simple derivative with respect to a parameter, is that the material derivative adds another convection term. As we see here, just this is more or less very complicated because all the spatial coordinates are summed up here. Writing it in a little bit simple notation here, we have here the sum over the spatial coordinates. And if we simply go to Einstein's index notation, where if we have two indices within the formula, we will sum up over these indices, and there we see it clearly that the material derivative itself is a sum over the partial derivative with respect to time, and here is the partial derivative with respect to the space coordinate, and it will be convected by this term. So this is the velocity, and that's what's a material derivative. Everyone got the material derivative?
I have a question to that.
Yes.
Why do you call it convection term, or what is meant by convection? Do you mean the change of of space in time, or how? Yeah, could you a little bit more explain what you mean by convection?
By convection. So this fluid particle in the fluid body has a spatial density variation.
Yeah.
So from one fluid particle to the next one, you have a kind of a density gradient.
Yeah.
And if now the fluid is flowing,
Yeah.
Just imagine like this, then the density variation will travel.
Mm-hmm.
So
And this is exactly the convection.
yeah, this is the convection.
Okay. Mm-hmm.
So
So the travel of the density in space, or the
yeah,
okay. Mm-hmm.
so you have kind of a density distribution in space, and this will be convected by wind or something like this.
Mm-hmm. Mm-hmm. Okay.
Probably imagine you have that jet going out of the airplane engine.
Yeah.
Then there is some mass added. So you inject fuel that is burned.
Mm-hmm.
And this fuel or added mass has some spatial shape. So you have some parts where the air is more heated, and some parts where the air is not so heated, and this air is then traveling.
Mm-hmm.
So you can also do this with the temperature. So
Mm-hmm.
for instance, as gave you the example with the jet, you can also do the material derivative of the temperature.
Mm-hmm.
So this is very similar.
Okay, but I think I got it.
Okay,
Thanks.
perfect. You're welcome. Anyone else? Any question? Okay. Perfect. Then we will proceed with the lecture. Okay. So you all got the impression what's a material derivative or substantial derivative or total derivative. So the material derivative, once again, is the sum of the partial change with respect to time and the convection. Okay, then in continuum mechanics, there is a very, so here again, you have the definition of the substantial derivative. That we have here the time change, and here the velocity, which convects the spatial change. As you will need it in the homework examples, this here is the Einstein's index notation. This is how it looks like. And the same term in terms of the operator notation looks like this.
Excuse me?
Yep.
So the line where it says substantial derivative, this is an operator.
Yeah.
Okay.
This is an operator. There is also in the lecture notes there is an appendix where there's a lot of math stuff you will find there. Yeah. You can see the lecture notes. Probably yes. Yeah, and there is also a lot of operator definitions and how you can compute stuff with that. So this will probably be useful for your homework. Good. Did I answer your question?
Yes, thank you.
Okay, perfect. So that's the how we distinguish Einstein's index notation and the operator notation. And now we come to a very important concept in continuum mechanics. It's the spatial reference system, or the observer formulation. So there are two opposing ways of defining your observer. The one is the Lagrangian frame of reference, and the other is the Eulerian. And so the Lagrangian is that the observer monitors the trajectory in space of each material point and measures its physical quantity. So, and in contrast to that, the Eulerian frame is in which the observer monitors a single point in space when measuring physical quantities. The measuring probe stays at a fixed position in space. So what does this mean? Probably we start with the Eulerian reference frame. And has anyone an idea of what it means? Probably no. Anyone wants to give it a try to explain it to the others?
Maybe I would formulate it like we learned it when we discussed wave equations. So at one point we are fixing time and looking on the change in more or less in space, and the other way around, fixing space and looking there how a particle or a value is changing in time. Is it more or less this?
Yeah, so the Eulerian framework is definitely fixing the space position.
Mm-hmm.
So you're sitting at a fixed position, and you're looking at what is traveling by, more or less. So that's the Eulerian framework. And the Lagrangian framework is like you are sitting in a boat. The Lagrangian framework is more or less you're sitting in a boat in a fluid and you're traveling with it. Yeah. Is probably a little bit complicated when you're imagining you're in a fluid. Typically the Lagrangian framework is used in structural mechanics. So this means, with respect to finite element modeling, that the finite element discretization moves with the structure. So if the structure deforms, your grid goes more or less with it. This is Lagrangian. Eulerian means that you have a fixed background grid, and the physical quantity is traveling through the grid. So it's more or less the difference. Yep.
Can I understand it like this? When I have a Lagrangian framework and I want to measure a sound field with a pressure probe, the pressure probe moves with the particles. So in essence, it travels with the sound. And
yes.
in the Eulerian framework, it's on a microphone stand.
Yep.
Okay.
That's more or less it. Because here in the Eulerian you have the trajectory. So this means more or less you are traveling yeah, with it.
Okay.
Yeah, and as these two systems are not enough, there is a very funny system, which is the combination of the two. Yeah, and it's called arbitrarian Lagrangian Eulerian system, and this is used if you're probably unsure of what you would like to use. So for instance, as we saw before, this fan simulations, this simulations like here, then the Ale formulation is used because it induces some grid rotation and some fixed grids, and then you have a combination of these two methods. But it shouldn't really bother you. Just imagine that you have here heard it, and if you're faced in your career at some point with kind of such a system, then you can go back here and check out the details. Good. Aaron understood the spatial reference systems. Okay, good. Then we will continue with it in a more formal way, as we will kind of represent it in a mathematical framework. If you have a Lagrangian reference frame, then the total change is the same as the partial change, because you're already traveling with your substance. In the Eulerian frame, the total change is the sum of the local change and the convective change. Yeah, and funny, the arbitrary Lagrangian Eulerian frame of reference, there the total change is also a local change with respect to the grid movement. So you are fixed on a grid that is moving, and you have a convective change, which is not the pure velocity how the particles are convecting, but it's the difference between the observer convection and the material convection. So this is very general, and if you kind of formulate it in this way and then introduce different convection differences, then you will obtain the Eulerian or the Lagrangian. So that's in all formulated in operator notation, and yeah, I hope it is clear for everyone. Any questions on that?
So did I get it right when I look at the arbitrary Lagrangian Eulerian ray
Yep.
or a reference system? Then this is the difference between the two velocities of the observer and the quantum or the value we want to measure. And
yes, yeah.
If this difference is zero, then we come to the Lagrangian frame more or less, because then we have the same velocity.
Yep.
And if we are staying at one fixed position, so the observer has no no velocity, then we get to the Eulerian frame more or less.
Yes.
Okay.
So you can, for instance, you know when you have an acoustic emitter and you have some receiver,
Mm-hmm.
And if the emitter or the receiver is traveling with respect to the other one, then you have kind of this Doppler shift.
Okay, yeah.
So this is how you can compensate the real frequency which is emitted, and what are the real kind of wavelength and stuff like this. So this is more or less a compensation. So if you have the emitter and the receiver are traveling with the same speed, they probably, you got it. They see the same as they're standing more or less at the fixed position. But if one of them is moving, then you have some convection.
Thanks.
Okay, good, perfect. Everyone got the concepts? Yes, I think so. Okay, then we will go in detail, or just would like to remind you about some functional analysis stuff. First of all, the gradient of a scalar quantity. I think all of you know what it is. Then we have the divergence operator. Everyone knows what's going on with the divergence. Yes. Okay, perfect. So all good. And probably not so familiar for you is the curl operator, but you probably heard it in electrodynamics. Okay, good, perfect. Yeah, and some other function analysis stuff is given in the appendix of the lecture notes, as I showed you already. So just check it out there, and yeah, I think the examples you can handle quite well. Okay, any questions on that? Should we do a 5 minutes break? All good for everyone? Okay. Then we will continue with the next stuff. It's the conservation equations. So we started with the basics. We're now heading to the conservation equations. So again, keep in mind that we apply continuum theory, and that we advance from that. A very important theorem for deriving the conservation equations is the Reynolds transport theorem. Everyone knows what it is? Probably not. Okay. So the Reynolds transport theorem is given here in the lecture notes, and it states that a total change of an integral quantity is the sum of a temporal change and some divergence part. That's the Reynolds transport theorem. It is in math, it's also kind of labeled Leibniz Theorem der Integralrechnung. So it looks a little bit different because in math they say, okay, the total change with respect to a parameter of an integral quantity can be expressed like this. So this is more or less the Leibniz rule of integrals. Yeah, and I think everyone heard it already. But anyway, you will have to do in the experimental section. You will have to derive this Reynolds transport theorem, and you can look it up in textbooks how you derive it, and there you get some additional knowledge about it, what it means, and stuff like that. Okay, so we assume that we know the Reynolds transport theorem, and we consider we then consider a scalar quantity mass density there. So, and this mass density is a relation from the domain across the time towards a quantity here, which is more or less the integral of that. So this is the representation where it maps. So here we have the scalar quantity, which maps the time and the spatial coordinate and the time to just a mass. This is now very abstract, but we will get to the mass conservation within a minute. And then we can derive this more or less through, and then we see, okay, the total change of the mass itself is a change of the mass density, or is related to a change of the mass density and some sourcing strengths of the mass density, which is also convected. This was now very complicated and abstract, and I will just head to the mass conservation, because this was more or less the explanation of the Reynolds transport theorem. So not bother with this slide. It's more or less complicated, and we will just jump into the mass conservation. So let's consider a scalar quantity like the mass density. Here the rho. We have here the kind of mapping from domain and time to the mass. So domain, time, mapping to the mass. And the mass is calculated by the integral over the control volume. Everyone knows what a control volume. It's just a concept where you fix some space and where you can integrate over it, and it has some continuous functions and stuff like this, and so that you can really integrate. Okay, so the mass is the definition of the mass. It's an integral over the mass density. Conservation of mass. Everyone knows what conservation of mass states. Probably one of you would like to explain it to the others.
Is it more or less that a system cannot gain or lose mass? So mass is constant in a system at every time?
Yes, unless you inject mass.
Yeah, of course, yeah.
So, okay, yeah, mass, as conservation already says, it is conserved, and typically the total change, as how it is conserved in mathematical terms, that the total change of the mass is 0. Now looks very very easy, but then you insert the integral into the mass definition here, And then you have the total change with respect to time of the integral of the mass density. Okay, very similar to what we had already here at the definition of Reynolds transport theorem. Then we can just apply here the Reynolds transport theorem and then arrive that the total change of mass, when it is 0, we can rewrite the whole stuff with this equation. And if this integral holds for every control volume, then you can just say, okay, this term in the brackets here must be fulfilled locally, and then you can derive the conservation of mass in the local form. So conservation of mass in the integral form is this here. Conservation of mass in the local form is this here. So it's, well, it's just the term here in the brackets and the 0 there from the conservation. And this is the conservation of mass of any fluid you can imagine. We assumed continuum theory. We also assumed implicitly that we have one species. So we have the mass or just air and no water, or just water and no air. But there are some fancy ways of modeling the two combined. For instance, if you would like to model rain or stuff like this, or humid air, or then there are special models which can capture that. Okay. Everyone got how we arrived at conservation of mass?
I have a question.
Yes.
Regarding the control volume. On the
Yes.
graph T, is this where the Lagrangian framework comes into play? Because I would imagine if we are in a Eulerian framework, I would not have the control volume as a function of time.
Yes, you will. This you will see then in the derivation of Reynolds transport theorem, that if the boundary is moving, then you will have some added terms there. And there's a trick during the derivation of Reynolds transport theorem that at one point you are at the Lagrangian frame, then you're switching to the other frame, then you can shift the two. Then you can shift the operator and the integral because it's not time dependent, and so on and so forth. So this is now not explicitly for any framework. It's just a general representation.
Okay.
It holds for the one and the other.
Okay, but why do I need to include some time dependence for the control volume?
Usually in the very restricted way that you just say, okay, the volume is always like it is. You don't have to do it. But if you would like to model more general things, like as we had the last time, the vocal folds, if you would like to model the vocal folds which kind of vibrating, then the domain is more or less time dependent. Okay. But as we assume one of the spatial reference systems, and we just restrict to one of them, then it gets simpler.
Okay.
There is the possibility that it gets simpler, but you will not benefit from it because usually the examples are not that simple, and you would like to have a general expression for your way of doing.
Okay.
Okay, did it answer your question?
Yes.
Why we still have time here?
Yeah, somehow. Thank you.
So just reframe your question, and I will
No,
try to. Okay.
maybe it becomes clear when we go further.
Okay, yeah.
Thank
So
you.
this time dependent is dependence of the control volume is just for that we seek a general formulation. So that's more or less the explanation. Okay. So deriving mass conservation in the integral form, then going to the local representation. We have here the mass conservation equation in the local form. So the time derivative of the density is compensated by a divergence part. This means if in one point the density fluctuates, it must be compensated by some spatial movement of the density. This means if you density fluctuations, imagine you have an emitter, like a sound source, kind of aims to fluctuate the density somehow. For instance, how can you fluctuate the density within a fluid? Anyone has any idea? Probably you have some laser beams which are kind of alternating the temperature in the fluid. Then as a consequence, you can alter the density, and this more or less heat bulb in the fluid then emits sound waves due to the second term.
So the second term is more or less a mass flux or a mass
Yeah.
spreading, or I don't know how to call it.
Yeah, it's some spreading. It's a spatial spreading of the density variation.
Yeah.
Exactly. Okay, and this is very general. This holds for any compressible fluid. Usually fluids are compressible. I've never seen an incompressible fluid, but there is a concept which is called incompressible fluids, which means that the density along the streaming trajectory is constant, or the density is constant in the whole space. It is a good assumption when the Mach number is below 0.3. So the Mach number is much smaller than 1, or Mach number squared is much smaller than 1. This is how we got to the 0.3 boundary of the Mach number. And there you can model a fluid as incompressible. But be aware, if you would like to simulate fluid dynamics and acoustics within one simulation, you always have to use a compressible fluid. So the incompressible fluid is just a mathematical concept which holds for Mach numbers below 0.3, and it assumes that we have infinite speed of sound, which is very unphysical because it also means that we have an infinite information velocity. Yeah, and this is very contradicting the physical theories, and yeah, I think everyone got it. That is a little bit obscure, but you can develop quite fast fluid dynamic models with using the incompressible fluid. So everyone got what happens with an incompressible fluid and when we can use it and what it implies for acoustics. So for acoustics, it implies that we have an infinite speed of sound. And if we have compact acoustics, also has in his theory that the speed of sound is very large and the wavelength is very large. And so in the whole nature, if you're using this incompressibility assumption, you also somehow assume that you have a compact acoustics within your simulation. So this goes very hand in hand. So incompressible fluid also means that the acoustics is more or less compact in the sense that the theories are the match. Okay, everyone got that? So I drive a short conclusion on the mass conservation. So we have an integral form of the mass conservation. We can derive for a general compressible fluid, the local conservation of mass, which is here. So temporal fluctuations is compensated by some spatial variations. And in the special case of Mach number below 0.3, we can use for fluid dynamics an incompressible fluid, which purely has or states that the divergence of the velocity is 0. Good. Keep in mind this equation. It's also quite important in the further discussion. And as we already pointed out, mass conservation, here we assume that we have no mass injection. So we have no mass sources in our domain, and that we don't produce at some point any mass. Okay. Any questions on mass conservation? Okay. Should we proceed or take a short break? Okay, then we proceed with the conservation of momentum. So in fluid dynamics, we have three conservation equations. One is conservation of mass, then momentum, and then conservation of energy. Every one of you knows what's the momentum. So the momentum is a vector, and it's the integral over the domain with respect to the density and the velocity. So the product density, velocity, and the integral over a control volume serves the momentum of a specific fluid. And here Newton related the rate of change of the momentum So the total derivative of this, you learned in physics, the sum of the forces equals the mass times the acceleration. More general, the sum of the forces equals the derivative of the momentum. And this is, yeah, Newton's second law. So in this reference frame, and it's stated like this. And again, inserting the stuff here, you will then obtain a similar formula as for the conservation of mass. Here the sum of the forces are, you have surface forces and you have some volume forces. So volume forces are, for instance, gravity or some electromagnetic forces. And surface forces are like the pressure, the imposed pressure on some body. Okay, having these ingredients, the definition of the momentum, that we can relate the change of momentum with the applied forces and what type of forces we have, we can then derive the conservation of momentum in its local form, again as we have it here. On the left side, it looks complicated, but it is not so complicated. Here we have again this quantity of the momentum. We also have it here, and it's kind of related to the velocity, as we also had it before in the mass conservation. And on the other side, we have the forces. The forces are the applied pressure on the boundary and the divergence of the stress tensor. Here we have the stress tensor and some additional body forces like the gravity or some electromagnetic forces. Okay, everyone got this? Any questions on the local form of conservation of momentum?
I have a question.
Yes.
In our lectures so far, the tensor or tensors in general did not occur. So could you please explain shortly what a tensor is?
Okay. So we have tensors of different rank. So there is 0, first, second, third. It's more or less the dimensionality of the concept. So a rank tensor 0 is kind of scalar, like this density. Then we have tensors of first rank, so which is more or less a vector. Here we have the velocity, and then we have this what is called tensor, is if you do the a metric, a product of two vectors. There are different definitions of products. Like you have an inner product, you have an outer product, you have some, it really depends on how you multiply the vectors. If you end up in kind of a math, as you did it in math, that the one vector is like in this notation and the other in that, and then you obtain a more or less matrix matrix is similar to the tensor concept. So you have additional entries for the different space, for the different space directions. So you don't have only the entry of the vector for the x direction. You also have for the x direction of the equations, you have some dependency on the x coordinate, on the y coordinate, on the z coordinate. This is more or less a very brief explanation of what a tensor is.
Okay, but I assume that there is some more to tensors because otherwise we would just call them a matrix, I guess. So what's the difference between a matrix and a tensor?
What's the difference between a matrix and a tensor? I have to say I'm not very sure about that, but usually a matrix is just a storing concept. A tensor is a physical concept of a field. So it depends on space, time. A matrix is just a representation. So you can represent the tensor via matrix, but a tensor also comes along with operators that you can apply on it. Like if you have defined for this matrix, so let's say matrix, if you have defined that you can apply the diversions onto this matrix, it's clear. But if you just have the matrix, it's not clear that you can apply operator to it. And the tensor per se comes with the definition that you can use operators to it, that you have a certain set of methods that you can apply to it. So for instance, if you have a tensor, that it is also more or less clear that you can apply Reynolds transport theorem to it. If you have a matrix, it's per se not clear because it's just a storing concept. So matrix is a mathematical concept that's just used also for calculations and stuff like that. A tensor is a more abstract way and a more physical way of doing stuff. For instance, here you have this called dyadic product. Yeah, and this is also related to the tensor. So you can relate two tensors via dyadic product, and then you obtain another tensor. For this dyadic product, I just did the reference to the appendix. It's not so important for the course right now. I think in one of the examples you're carrying out, you just have to do this dyadic product and kind of go from the operator notation to the index notation. And this is a dyadic product in the index notation is written like this. So you here have the vector of the velocity.
Could you please share your slides again? You're not sharing right now.
Okay.
Don't know why. Switched at some point.
So I will stop the recording.